Hey everyone, this is Dr. Aeronautics, and this is I believe it's the third tutorial. Yes, we're going to be doing some high altitude testing. So before we do that, we need to go into some theory beyond what you might know for an airplane. In an airplane, you have four forces, lift, weight, thrust, and drag, and both are very similar at 30,000 feet than they are at sea level. Now we're going to try taking this thing up to about 75,000 feet, which is about 24 kilometers, and we're going to see what happens when we do that. So basically there's three concepts we need to go into. One of them is primary response of the air flight control surfaces. One is the secondary response of the air flight control surfaces. And then the third is thrust. So I'm actually going to start with thrust. So a lot of people think that, and I don't know why, rockets don't really work well in space. Because the way rockets work is you have a thrust chamber in here. Those would be under where this radiation symbol is. The hot gases get reacted and they get pushed out the back super fast, causing all the air that's already here to get pushed back, and essentially we're pushing on the air. That's not how it works. And in fact, the way rockets work is by throwing mass out. An example of this is getting a really efficient chair. If you've ever had one of those office chairs where you just give the table a slight tap and you go rolling for the next 5 seconds. Imagine you had a bag of bowling balls and you're just going to hurl those off your chair as fast as you can. What do you think is going to happen? You're going to go flying in the other direction. That's exactly what this is. The only difference is, instead of huge bowling balls, you have very small molecules of mass, but they're being accelerated outwards at like 3,000 miles per hour. So because impulses momentum times time, or I believe it's momentum. Yeah, momentum times time. One of the two. Either way, momentum is mass times velocity. So you have a tiny mass, but you have a huge velocity, so great, in fact, that we go forward at a huge rate. So that's how a chemical rocket works, and that's the principle behind pretty much every rocket. So what does this mean? When we go into lower atmospheres and into space, then we're not affected, right? Wrong, because the atmosphere actually has a secondary effect. The thrust chamber generates a static thrust, and the speed of the outcoming air depends on the pressure outside, right? Because let's say that the thrust chamber in here were about 400 kilopascals or 4 atmospheres. Pressure wants to flow from high to low. If the pressure outside the craft were also 4 atmospheres, what do you think would happen? Nothing. We would get a flame in the combustion chamber, and it wouldn't go anywhere. It would just burn out. In 1 atmosphere, actually, let's go to 2 atmospheres. What do you think would happen? The pressure difference of 4 to 2 would cause the gas to come out of here fairly quickly. What about 4 to 1? Yeah, it would come out fast. What about if there's vacuum in here? Like, let's say we're space. 4 atmospheres, no atmospheres. It's going to come shooting out. So the answer to that is rockets actually do better in space. Our rockets will actually gain traction as we go higher and higher and higher. So that's all the rocket theory you need to know for now. Okay, so the first thing I want to talk about is the primary response of the air flight control surfaces. Let's turn them on. Okay, so the air flight control surfaces, you have the elevators, or in this case it's the ailerons, because we also have ailerons working as elevators. And then we have the rudder. In this case we have a double rudder, because we have a I don't know if it's bi-rudder. The Delta Wing aircraft that we have has two rudders. So basically, now these actually do work off the principle of deflecting air. So there has to be air in order for us to deflect. They have to push against air. They're not deploying their own air. So in the case of the rockets, don't really work, people. You know what really doesn't work? Air flight control surfaces. I'm not kidding. Like, when we go into space, I could do this all day and nothing would happen. Nothing at all. So what happens when we're at 75,000 feet, which is about 22.8 kilometers, where the density ratio is about 7.5 times lower than it is at sea level? That means that our response is going to be about 7.5 times lower. If we're going the same speed that we would be going at sea level, we could travel at the square root of that, because these work off the drag principle. These induce a directional drag, which causes us to change direction. And if you take the square root of that, you'll get the speed that we need for the same dynamic pressure. So take the square root of 7.22, and we get a density ratio of 2.68. Now, if I multiply that by 250, which is a good speed to go out at sea level, we'll need to be traveling about 672 meters per second to have a good response at 75,000 feet, which is 1,500 miles per hour. And that's about right, because the SR-71 Blackbird would travel about 1,500 to, or no, am I off? Yes, I'm off. The SR-71 Blackbird would travel about 2,500 miles per hour and possibly faster. I still don't think they've released the numbers. Okay, so this is the secondary response. So the primary is with this, but the secondary is once we start turning, what's going to cause us to stay in the direction of flight? What's going to stop us from just rotating out of the direction of flight? The answer is nothing. So as we're at 75,000 feet, what we're going to notice is the aircraft will start to turn off of our prograde velocity vector. Let me slide forward so you can see that real quick. Although, let me change the, put the HUD on. It's already the color we like it. By the way, we're still at Barksdale Air Force Base in Shreveport, Louisiana. I haven't moved us at all. It's your fault. That's right. I'm blaming you for me being here. But this actually puts us in a good position to come back to KSC much, much faster. And KSC is... So there's the North Star. That's how I know where north is. And I'm in Louisiana, which means I'm west of Cape Canaveral, which means I need to travel east. So go down about 90 degrees, and here's a good test. We got Taurus and I think Orion. Yeah, Orion's out of view. That's gonna, well, it will come into view because things rise on the eastern front. So maybe we can see Orion. Basically, one of the things I want to pay attention to is stars. Once you get above 60,000 feet, things change drastically and you can start to see stars. Alright, so let's go roll forward just a bit. Okay, that cross there, that was our prograde velocity vector. So what we're going to find is once we start getting higher, that will start to digress with our airplane symbol, which represents the location of the nose. So this is very important for maneuvering You don't want to lose control of the air of the spacecraft when it starts to become a spacecraft. It will ruin your ascent. So what I'm going to do is I'm going to go up to about 12 kilometers, and that's going to be our starting point. We're going to use that as like our proof of concept. Okay. And if you notice, the fuel is almost empty, so we're actually going to refuel that. So we press F4 to bring up the display here. Now if I go to function and scenario editor, okay, it will open our scenario editor, select our craft, the GL01S, that's us, okay, edit. Now we want to go to propellant, click propellant, drag this slider. Well, actually, you know what? Easier. Just click full. Done. Scramjet's full. Tank 2, 1611.51. That's going to be our main fuel. Click full. Done. Apply. Done. Done. Close. And F4. Okay, we've just refueled. We have a more realistic way to refuel in the Delta Glider 4 and the XR2 Raven Star, which is why I like to fly those. All right, the next thing, let's get our map up and target the. So what I'm doing here, powering on the MFD, select surface. Actually, I don't want surface. Select map, track, zoom all the way in, and now I want target, spaceports, and find Cape Canaveral. Enter. Okay, now it's selected Cape Canaveral for us. I'm going to zoom all the way in so you can see how the horizon changes as we go up. Now I'm going to power this on. And now I'm going to select surface. And we'll do ground speed, but I'll flip back and forth between indicated airspeed so you can see the differences. Okay, two very important numbers to watch. I'm not sure if my cursor is visible, but if you look at the surface MFD, you'll see the primary flight display. That's the airplane on the artificial horizon. Then under that, you'll see a pitch and bank indicators. Then under that, you'll see a section bounded by green lines called ATM data. And you'll see the OAT, that's the outside air temperature, not that important. M for the Mach number, not that important. DNS, that's the density. Watch density as we start going up, that will decrease. STP, that's static pressure, that will also decrease. DNP, that's our dynamic pressure, and that will increase or decrease based on the static pressure and our current Mach number. Okay, so I think what I'm going to do is save the scramjets if I can help it, and then we'll do a scramjet demo next time. I shouldn't have to use them because the higher the craft goes, the more efficient our fuel gets, for the reason I described earlier. Okay, so we're going to take off and then perform a few demonstrations. Watch the dynamic pressure increase as we start to accelerate. Okay, I don't have once again, I don't have GPS control, which means I'm going to have to reconfigure this. Okay, so I just demonstrated an aborted takeoff. So that kind of gives you the kinds of speeds that you can reach before it's not possible to stop the craft on the runway without the use of retro thrusters. But that's probably not a good idea in the atmosphere. Unless you're in Mars, which is extremely thin. Alright, so what I'm going to do now is turn the craft around, and we'll take off the other direction. I do kind of like it how you can see the curvature of the runway because of the unflat surface. Runways in the real world aren't 100% flat. Here we go. I see the GPS response working now. And like before,
retracted.
Oh man, I can't wait to stop using this thing. Alright, so we're now at 1,000 feet in altitude. So let's check everything out, right? So the little airplane there represents where we are now. The crosshair represents where we're going. If those aren't close together and the air pressure's high, we can have a spin out. So let me demonstrate a few things. What I'm going to do is pitch the spacecraft full up and full down, and you can watch the response. So there's full up, and it follows, but it takes some time. And there's full down. Again, follows, but takes some time, and it's okay. So now I'm going to do full rudder. There's full rudder to the left, and we didn't have a spin out, good. And full rudder to the right, and we didn't have a spin out. So now notice how, ouch, we're actually traveling this direction, but look at what happens when I change this. We're actually sliding. This is a pretty good demonstration of what happens in space. We're still traveling forwards, even though we're sliding, we're traveling sideways, in other words. Okay. The last thing I want to show you is the ailerons. So here's a full left bank, and just look at how long it takes to stop, okay? And let's do a full right bank and see how long it takes to stop. Okay, about 40 degrees. Not too bad. Alright, let's go to 30,000 feet. Meanwhile, I'm going to look at this ticker tape here, and we need to go to 105. That will get us to the Kennedy Space Center. So I'm going to go to 12 kilometers, which is 40,000 feet. Let's see if the constellation Orion is becoming visible. Not quite yet. Oh, there it is. Yeah, it's coming up now. Oh, man. Is this still going on? I'm going to have to disable the heading hold because the autopilot doesn't understand how to... I know what's going on. Okay, so what's going on? Look at our speed, 180, and the static pressure is now 1/3 of what it is at sea level. So guess what? This is what happens when you come up high and you don't accelerate. Look at the response. It's atrocious. So what do we need? We need more speed. That was my fault. So look at our angle of attack. That's 6 degrees. That would stall a regular airplane. We want to get that under 2. There we go. That's looking pretty healthy. Okay, so we're at 40,000 feet, and like I said before, you know, the sky color is going to change like it always does in an airplane. If you're really, really, really attentive to it, you can look almost straight up and see that the color of the sky becomes a little bit more crisp of a blue. I'm thinking about modding the color of the Earth sky, because even though realistically in terms of brightness, it's more of a rich blue. It's not like the gray blue that you see here. But I think that's done because it looks more realistic once you get into space. Alright, so I'm putting the auto throttle on now. The angle of attack is a good indicator of how fast we're going versus how fast we should be going. If it's above 2 degrees, that's not good. If it's above 5, that's really bad. If it's above 10, you're probably going to stall or spin. Alright, so we're heading in the right direction now. So for now, we are at 40,000 feet, which is the altitude that most people have been at before in aircraft. So what I'm going to do is I'm going to disable the autopilot now, and we're going to exhibit a few things. Here's full pitch up. Watch the response. Pretty good. Here's a full pitch down. Response is pretty good. Full left, a little bit slower. And full right. Okay. Now full roll left. Okay, just about the same. And full roll right. Yep, so nothing's really changed except our speed. So we were at about 20 kilopascals of dynamic pressure up there. Let's go ahead and put the autopilot back on to recover us. Okay, so not really much has changed. Now the kicker is I'm going to go up and I'm not going to change the speed, and you can see as things start to happen, what starts happening. There's going to be a lot of bright stars coming up this way pretty soon. And once we level our wings, we will start ascending. So now, why can't most airplanes go higher? Well, their engines are fed by oxygen. So what happens is you go higher, there's less and less oxygen. And eventually, if you go too high, the engines will shut down. Alright, so we've pretty much recovered. So I'm going to disable the autopilot now. We're going to go up to full throttle, and I'm going to pitch the nose up. Okay, we're at 45,000 feet. This is the maximum altitude that the 747 can attain. We're at 50,000. $60,000 feet. $70,000 feet. Now you can see the sky is quite a bit darker. And also notice how quickly we did that. Oh, is that the Mississippi River? I think it is. So there's the Mississippi from 70,000 feet. There are videos from U2 pilots. I'm going to set this to hold our current altitude. So we want 21.3. Alright, so our angle of attack is less than 1 degree, and we're doing 891 meters per second. So let's slow down to 672, which is what I said we would need in order for the same behavior at sea level. While we're doing that, so in the U2 videos, this is about what you would see from a 70,000 foot video. And you can see panorama up here. And you can start to see there are a few stars that we can see. Notice how long it takes us to slow down, even though we have no throttle. This is because at a static pressure of 4.5, we basically have 1/20th the pressure that you would have at sea level. Okay, so we are now at the proper speed. So let's exhibit a few things here. First of all, we have reduced lift, but let's do full up, full down. So you notice how the response is changing? Full left. There's Orion. See what I mean about the bright stars? You can see almost the whole of Orion right there. In full right. And now let's try the aileron, see what happens. Slower response. So now what happens if we pitch up and go even higher? You notice how it's starting to become hard to control the aircraft, spacecraft. Well, it's an aircraft that's becoming a spacecraft. I'm also letting my speed too far down. That's cheating. So in real life, airplanes could do what's called a zoom climb. In the 1950s, when they had aircraft powerful enough to perform one, such as the F-104 Starfighter, what they noticed is when you pitched up at a high velocity, suddenly you would lose all your control. So let's pitch up and see what happens. Watch our static pressure drop. Also, listen. Where has the sound gone? It went with the air. We're at 24 kilometers, which is 80,000 feet. We're losing lift, and we're also losing control slowly. So what do you do to control the aircraft through this controlled zoom climb? The answer is with a reaction control system.
Rotation.
Now watch. Hear the rockets firing? We have a lot more control. We're actually doing a zoom climb. We could have turned on the engines and continued it, but I'm continuing the zoom climb. So what pilots needed to do was keep the prograde velocity vector in line with this airplane, or you will spin out. So what's doing this? You have a pair of rockets. The rocket pushes air one way, and we go the other. That's how reaction control system works. And now we're doing what's called a re-entry, so we can actually turn this off to save fuel. You want to know when to turn that on so that you can save your fuel. If you're really careful with it, then you know exactly what to do. Now look, we've just descended to 55,000 feet, and now the stars of Orion have disappeared magically. Let's do a steeper zoom climb and demonstrate the absolute need for this. I'm actually going to spin out of control. But I'm going to regain control because I know how to use the reaction control system. So what's going on? We're at 200 meters per second, and which is way too slow for 19 kilometers, which is about 60,000 feet again. And I actually have full right stick, and nothing's happening. So this is a slight loss of control situation. I can't control the aircraft's orientation to the degree that I should. Let's turn on the reaction control system again. And look at how quickly I gained control. So now we're doing re-entry again. And when in an aircraft, you would hear this too if you were doing a zoom climb.
Attitude off.
We're now down to about 30,000 feet, so I'm going to add engines in again. And then we'll do a cruise at 80,000 feet until we get to KSC. Okay, everyone, that was how to fly at higher than normal altitudes, normal being airline altitudes. Next time, I will demonstrate the scramjet above 100,000 feet. This has been Dr. Aeronautics, and I will see you guys next time. Bye-bye.